Gnanam paramam dheyam. Knowledge is supreme.
Friends, we have been looking at predicting the conversion in a non-ideal reactor provided the RTD function is known. So, there are two types of models that we are going to discuss. One is the segregation model, the other one is the maximum mixedness model, and these are two extremes which actually provide a bound for the conversion depending upon what is the order of reaction and the kinetics of the reaction which is conducted in the reactor. So, these two extremes are the early mixing model regime, or early mixing, that is one extreme, and the model that represents early mixing is the complete segregation model. While the late mixing, which is the other extreme, that represents the maximum mixedness model. So, these two extremes essentially represent the two levels of mixing, where the two levels of mixing of the macrofluid globules that we actually defined in the last lecture. So, let us look at the first one, the segregation model of a reactor. Now, suppose let us consider a Cstr. So, let us consider a Cstr, a tank reactor. It could actually be any reactor, and let us assume that the fluid elements of different ages, they do not mix. That is the segregation model, and which means that they remain segregated all through. They remain segregated all through, and the flow is essentially like a series of globules, where one globule enters the reactor at a certain time, and that spends some time. Another globule which enters at a different time, the age of that particular globule is going to be different, and which means that the globules of different ages, they do not mix with each other. So, flow is essentially a series of globules, and we may assume each globule as a batch reactor because it does not mix. So, whatever reactant which is present in this globule, it continues to undergo reaction as long as all the species which is present in that globule is gradually going to complete conversion. So, therefore, each globule is considered as we may consider that as a batch reactor. So, now how do we model this? So, we can actually depict this depict this particular aspect in a Cstr as basically a tank which contains several globules, and each of these globules are now going to have different ages. So, that is going to have a different age, this is going to have a different age, and this is going to have different age, and each of these globules can actually in principle be of different sizes as well. Properties that are of these globules will be that they will be of different sizes, and then more importantly, because they do not mix, each of these globules is actually going to retain their identity. They are going to retain their identity, and there is no exchange between globules. So, there is no exchange of molecules or matter between different globules, and each of these globules will continue to maintain its own identity. Now, one may also depict the same picture, a similar model in a plug flow reactor. Suppose we have a continuous flow plug flow reactor. So, suppose if we model a continuous flow system of which is a continuous flow system of the non-ideal reactor as a plug flow reactor. Suppose if we model this as a plug flow reactor, then if you want to incorporate a segregated model for this non-ideal reactor, this may be depicted as follows. Suppose if there is a tube, and if there is a fluid which is flowing at a certain volumetric flow rate V naught into this tube, and if the volume of the tube is V. Now, instead of the fluid leaving from the other end of the reactor directly, the fluid can actually be taken out from the side of this tube at different locations along the side of the reactor, and they can all be joined together, and together they actually leave the reactor. So, now, each of these streams, because they are withdrawn at different locations, each of the globules will actually have different residence time. So, the location where the fluid is actually withdrawn from the reactor can actually be decided based on the residence time distribution of the actual non-ideal reactor. So, suppose if this is the residence time distribution, if that is the residence time distribution, and that is the E curve, which is the RTD function, which is actually measured experimentally of a real reactor, then based on this RTD function, such kind of a withdrawing of the fluid from the reactor can actually be designed. So, the fluid which is actually withdrawn from the reactor right at the entry location is going to have the shortest residence time, and the one which is actually withdrawn at the other end of the reactor is going to have the longest residence time. So, that is going to have a long residence time. So, therefore, what we have done is we have removed batches of fluids from different locations inside the reactor, and the location from where it is withdrawn is actually specified by the residence time distribution function E of t, which may be measured experimentally for a non-ideal reactor. And because we are withdrawing from the side, there is no interchange of molecules between each of these globules when they are actually present inside the reactor where the reaction actually occurs, and each of these can actually be considered as actually a batch reactor. So, what it suggests is that the mixing for this kind of a system, as actually the fluid appears as a well mixed system when it enters the reactor, but when it leaves the globules are actually completely segregated. So, therefore, the reaction time in each of the batch reactors, that is each of the globules which may be which is basically withdrawn from different locations along the side of the reactor, that time, the reaction time of batch reactor of each of the batch reactor is equal to the time spent in the reactor. So, this is the reaction time spent by each of the batch reactors. Remember that every location from where the fluid is actually withdrawn from the side of the reactor, that globule can actually be considered as a batch reactor, and the time that is spent by the reaction time of each of these globules, that is each of these batch reactor, is equal to the time that it actually spends in the reactor itself. So, therefore, the mean conversion, if x bar is the mean conversion, that is equal to the average conversion over all globules. So, what is of interest is essentially this mean conversion. So, we want to predict the conversion of the reactor, and what we essentially need to predict is this mean conversion from the reactor. So, how do we find this mean conversion? So, the mean conversion of globules with residence time of a certain time interval dt. So, let us say that the mean conversion of globules with residence time between t and t plus dt in that small interval of time. If that globule has a residence time in this small time interval, then that is essentially given by the conversion achieved by a globule after spending t amount of time in the reactor, and that multiplied by the fraction of globules with residence time between t and t plus delta t. So, that is the abstraction of how to get a mean conversion of globules with a certain residence time between t and t plus delta t, which is essentially the conversion achieved by the globule after spending that time t amount of time inside the reactor multiplied by the fraction of the globules with that residence time between t and t plus delta t. So, now if we put the corresponding expressions corresponding to each of these terms in the mean conversion, we will find that dx bar, which is the mean conversion of the globules whose residence time is between t and t plus delta t. So, that should be equal to the conversion achieved by a globule after spending that time in the reactor multiplied by the fraction that has a age between t and t plus delta t. So, therefore, from here we can write that dx bar by dt, which is the mean conversion, that is equal to x t into e of t, and therefore, x is equal to integral 0 to infinity x of t e of t dt. So, remember that the x of t, which is actually present inside the integrand, that is essentially the conversion in batch reactor. Because we consider each of these globule as actually a batch reactor. So, that is the conversion as though it were a batch reactor, and that multiplied by the corresponding residence time distribution integrated over all residence times will give the mean conversion. So, let us consider a first order reaction. Let us consider a first order reaction where A goes to products with a rate with a specific reaction rate K. And for a batch reactor, the performance equation is d minus dNA by dt, that is equal to minus Ra into V, where V is the volume of the reactor, and let us assume that it is a constant volume system. And so, now we can use the relationship between the number of moles with the corresponding conversion, and we can rewrite this equation as Na naught into dx by dt, that is equal to minus Ra into V, which is equal to k Ca naught into 1 minus x into V. And so, from here we can easily decipher that the conversion is equal to exponential of minus k into t. And remember that the Ca naught into V is essentially equal to, that is equal to Na naught. So, therefore, the conversion as though conversion in each of these globule is given by 1 minus exponential of minus kT. And so, from here we can now find out what is the mean conversion. We know the mean conversion is equal to integral 0 to infinity, that is over all residence time of the product of the conversion in the batch reactor multiplied by the corresponding residence time. So, therefore, x bar is equal to 0 to infinity x of t e of t dt, and so that is equal to integral 0 to infinity 1 minus exponential minus k t e of t dt. Now, suppose if the reactor is actually a plug flow reactor. So, suppose if it is a plug flow reactor, then the residence time distribution E of t is simply given by the delta function of t minus tau, where tau is the space time of the reactor, which is the ratio of the volume to the volumetric flow rate of the reactor. So, now for a plug flow reactor, it will simply be 1 minus integral 0 to infinity exponential of minus k t into delta function t minus tau dt, and that is nothing but 1 minus exponential of minus k into tau. And k into tau is essentially the dimensionless quantity called the Damköhler number. This is the Damköhler number, which is the ratio of the space time to the reaction time, and so we can write this as exponential of minus dA. So that's the mean conversion that would be achieved if it were to be an ideal plug flow reactor. And what is interesting is that the model that we actually obtained from the segregated model is actually same as that of the mole balance of the plug flow reactor. We know that from the mole balance of the plug flow reactor, the performance is actually performance equation suggests that the conversion is actually equal to 1 minus exponential of minus dA, and let us see how that is the case. So, the mole balance of a plug flow reactor on species A is nothing but dx by d tau, that is equal to k into 1 minus x, and therefore, x is equal to 1 minus exponential of minus k into tau, which is equal to 1 minus exponential of minus dA. So, therefore, the conversion that is actually achieved by using a completely segregated model is actually exactly equal to the conversion that is achieved by an ideal plug flow reactor if it were to be a first order reaction. In fact, we observed this in one of the lectures before, that we mentioned that if it is a first order reaction, then it does not only RTD function is sufficient to estimate the conversion, and the level of mixing actually does not play any role. So, we will see in a short while as to why that is the case. Now, before we look at that, let us consider if it were to be a Cstr. So, the residence time distribution function for a Cstr is given by 1 by tau into exponential of minus t by tau. So, therefore, x bar, the mean conversion, plugging this into the integral and integrating the expression, shows that x bar is equal to tau into k divided by 1 plus tau into k, which is equal to the Damköhler number divided by 1 plus Damköhler number. So, now if we write the mole balance for a Cstr, so the performance equation for the Cstr is the mole balance on A is Fa naught, which is the molar flow rate of the species at inlet, that is multiplied by x is equal to minus Ra multiplied by V, that is equal to k into Ca naught into 1 minus x into V. And minus Ra is the rate of generation, minus Ra is the rate at which the species is actually being consumed. So, from here we can see that x is equal to tau into k by 1 plus tau k, where tau is the space time of the reactor, 1 plus dA. So, clearly you can see that the conversion achieved through a segregated model is actually exactly same as the conversion that is achieved from the performance equation of the ideal Cstr. So, this suggests that for a first order reaction, the information of RTD function is actually sufficient, and the degree of mixing is not going to add any additional information, and the RTD function itself can be used to predict the mean conversion of the reactor. Now, the question is, why is that the case? So, the reason is the complete mixing or segregation actually makes no difference for first order reaction. This is because the rate of change of conversion actually does not depend upon the concentration of the reacting molecule. So, the rate of change of conversion independent of concentration of the reacting molecule. So, this is the reason why for a first order reaction, the RTD function alone is sufficient to predict the conversion that is achieved by the non-ideal reactor. So, the rate of change of conversion is independent of the concentration of the reacting species. That explains why for a first order reaction, RTD function is sufficient to estimate the conversion of the reactor. So, now let us extend this to a laminar flow reactor. LFR stands for the laminar flow reactor, and the residence time distribution is given by 0 for t less than tau by 2 and tau square by 2 t cube for t greater than or equal to tau by 2. So, that is the residence time distribution for a laminar flow reactor, which we have actually derived in the previous lecture. In the normalized form, E of theta is equal to 0, 1 by 2 theta cube, and this is theta less than 0.5 and theta greater than or equal to 0.5. So, now we can plug this distribution into the conversion equation, and we can find that it will be equal to 1 minus 0 to infinity exponential of minus k into t into E of t dt, and that is equal to 1 minus integral 0 to infinity exponential of minus k tau theta into E of theta into d theta. So, on performing the integration by substituting the corresponding distribution, one can find that the mean conversion in a laminar flow reactor is essentially given by 1 minus 0.5 into the space time multiplied by the specific reaction rate into exponential of minus 0.5 k tau minus 0.5 k tau the whole square integral 0.5 to infinity exponential of minus tau k theta divided by theta into d theta. So, that is the expression, and if one solves this integral, one will be able to find out what is the conversion in a laminar flow reactor. So, let us now compare the mean conversion that is achieved using these three different types of reactors. So, if we plot as a function of the Damkohler number, which is the ratio of the space time to the reaction time x bar. So, the Cstr would actually be like this, and the plug flow reactor would actually predict a much higher conversion for a first order reaction. Remember, this is for a first order, and the laminar flow reactor would be somewhere in between. So, the plug flow and the Cstr, they sort of provide a bound for the predict conversion of the first order reaction in a non-ideal reactor, and such kind of graphs actually can be generated for such kind of plots can be generated for reactions of other orders and other types of kinetics. So, what it suggests is that for a first order reaction, the extent of mixing not required, while for other reactions, other kinetics, extent of mixing plays an important role. So, extent of mixing actually plays an important role, and it is required in order to predict the conversion of the non-ideal reactor.